Whenever you're on one of those huge video calls, have you ever just stopped and thought, how on earth is this actually working? I mean, how are thousands, maybe even millions of us all connected in real time without the entire internet just collapsing? Well, today, we're going to pull back the curtain and look at the incredible system design that makes it all happen.
All right, so here's our game plan. First, we're going to start with the most basic challenge, just getting two computers to talk to each other. Then we'll figure out how to get through firewalls. After that, we'll see why that first solution kind of hits a wall when more people join, and how a server can save the day. And finally, we'll get into the actual language these systems use to talk to each other so fast.
I mean, this is really the heart of the problem, isn't it? It's not just one person talking to another. It's about creating the shared live space for a massive number of people, and every single one of them is on a different network with different conditions. It's this gigantic scaling puzzle, and we're going to solve it, piece by piece.
Okay, first things first. Before we can even dream of connecting a million people, we've got to connect just two. And you know what? That's actually way harder than you might think. You can't just call up another computer directly on the internet. Let's dig into why that is.
You'd think it would be this easy. I mean, every device in the internet has an IP address, right? So why can't we just point our video stream from my address to your address? Well, it's because the address my computer uses here at home isn't the one the rest of the internet can actually see. And this is where it gets really interesting. Your computer has what's called a private IP. The best way to think about this is like your apartment number. It only makes sense inside your building. The outside world, the internet, only sees your building's public IP, which is like the main street address. And you just can't send a letter from across town directly to apartment 5B. You need that street address first.
So your home router, it basically acts like a doorman for your entire network. It uses a process called NAT, Network Address Translation. It handles all the mail going out, but for security, it won't let any random uninvited mail in. And that's great for keeping you safe, but it's a huge problem when you're trying to start a video call with a friend.
So NAT is our first big roadblock. We need it for security, but it's blocking our direct connection. Luckily for us, some really clever engineers came up with a workaround to kind of punch a temporary hole through that digital wall.
So we bring in a third party, something called a stun server. Now the full name is a bit of a mouthful, but its job is unbelievably simple. It's just a server out on the public internet that does one thing and one thing only. It tells you what your public address looks like to the outside world.
And this quote just nails the concept. When you make a phone call, caller ID tells the other person your number. A stun server is basically that, but for your computer. You send it a tiny packet of data, and it acts like a mirror, reflecting back exactly what public IP address and port your router assigned to you for that one connection.
Okay, so here's how it works in 4 simple steps. First, your app just pings the stun server. Second, the server looks at the request and just reads your public IP and port from it. Third, it sends that info right back to you. And now, the magic part. You and your friend share those public addresses with each other, and bam, you can connect directly. It's like you've just created a temporary private tunnel right through the internet.
Fantastic. We did it. We connected two people directly. This kind of setup is called a mesh network. It's fast, it's efficient, it's perfect for a one-on-one chat. But what happens when the call starts to grow? What happens when we add a third person, or a fourth, or a 10th? Well, that's when our beautiful, elegant solution starts to fall apart.
See, in a mesh network, every single person is connected directly to every other person. For a 3-person call, that's totally manageable. Your computer is sending out 2 video streams and receiving 2. And because the data is traveling the shortest possible path between you, the latency is incredibly low. Everything just feels snappy and responsive.
But this is where the math gets absolutely brutal. In a 10-person call, your computer has to encode and upload 9 separate video streams. If each one of those streams is, say, 2 megabits per second, you're looking at 18 megabits of constant upload bandwidth. Most home internet connections can't even handle that. Your CPU is screaming, your laptop fan is going crazy, and the call just grinds to a halt. The mesh model, it just doesn't scale.
So the crucial takeaway here is that for larger groups, we need a totally different architecture. The whole decentralized idea of a mesh network actually becomes the bottleneck. So to solve this, we bring in a powerful central server to act as a kind of hub.
And this slide right here lays out the fundamental trade-off. A mesh network gives you the best possible latency, the fastest connection, but it absolutely crushes your computer and your internet connection. A central server, on the other hand, takes all of that heavy lifting away from your machine, but it might add a little bit more delay, since your video has to go all the way to the server and then back out to everybody else.
It's the classic system design dilemma.
The modern solution to this is called a Selective Forwarding Unit, or SFU. The best way to think of it is as an intelligent traffic cop for video streams. You send just one video stream up to the SFU, and it does all the hard work of forwarding it out to everyone else in the call. This just massively reduces the load on your computer, and it's the real key to scaling calls up to hundreds or even thousands of people. It's the kind of tech that powers services like live.
So, we have our architecture, right? We use a mesh for small calls and an SFU for big ones. But there's one last piece to this puzzle. How does the data actually travel? It turns out the language of the internet, the protocol you use, is absolutely critical for real-time video. This quote gets right to the heart of it. In video conferencing, the #1 absolute top priority is speed. If a tiny little piece of a video frame gets lost on the way, you know what? We don't really care. We'd much rather just skip it and get the very next frame that's closer to what's happening right now. A tiny glitch is always better than a long, frustrating delay.
And that brings us to the two main protocols of the internet, TCP and UDP. TCP is like sending a text message. It is super reliable, it guarantees every single packet arrives, and it makes sure they're in the correct order. If one gets lost, it stops everything and resends it. That's perfect for a chat message, but it's awful for video. UDP, on the other hand, is like a live video stream. It's all about speed. It just throws the packets out there and doesn't look back. If one gets dropped, who cares? The next one is already on its way. That low overhead is what makes real-time communication possible.
So let's just recap the whole journey. We started by punching a hole through firewalls using stun. Then we built these really intimate, super low latency calls with a mesh network. But when the party got bigger, we brought in the heavy lifter, the SFU, to manage the crowd. And this whole system, which is often powered by an open source technology called WebRTC, is smart enough to use UDP for speedy video and TCP for reliable chat. It's this beautiful symphony of technologies all working together to solve a really massive problem.
And that brings us right to the future. We've built this incredible system for human-to-human connection. But what's happening now is that AI agents are starting to join our calls as actual participants. They're listening, transcribing, making summaries. So how is that going to change the architecture we just designed? Will the SFU need to get even smarter, forwarding streams not just to people, but also to specialized AI services in real time? That's the next big, exciting question for the people building our connected world.